x squared minus 1, right?
Yeah.
Did we do that right?
Yeah.
I think we did that right. And if we didn't, it's your fault, right? That just wasn't that terrible. You're never going to see two variables. That's not a thing. We started this by using simple numbers. You guys drew a picture. You went, oh yeah, that's just like baby trig, right? We find all the trig functions by just coming up with the appropriate triangle, and that seemed really, really simple. And that really is simple. But then I threw in a variable and you realize nothing really changes. But now I'm making my answers functions as opposed to just values. Before, what we were given, we were figuring out a value, one simple ratio that worked. Now we're figuring out a function that is always true. Okay, that's kind of a powerful thing. Okay, any questions so far? Want to do a couple more? Let's try a couple more.
Do you even need to like draw anything really?
Oh, do you know the answer already?
I'm wondering if there's like lesser things because.
Well, if I said, hold your thought for a moment. What if I'd asked this question? What is the answer to this question?
Ratio x over 5. 3x over
You all agree it's 3x over 5?
Yeah.
Yes.
I can see your mind working right now.
I see.
So what do you think the answer to the other question is?
5 over 3x.
But you ended it with a question.
5 over 3x.
5 over 3x. Is she right?
Yes. Yes.
Yes. Can I still draw the picture to prove it to myself so I don't have any doubts?
Yeah.
Yeah.
You are correct. I purposely chose something that had that relationship. This, by the way, this is the more important of the two. Any function of its, but this is an absolute across the board, always true mathematical statement, no matter what it is. Isn't that always true? You learned that, hopefully you learned that in remedial algebra. The function of the inverse function of the input is just the input back again. So I have certainty that this statement is true, and secant is the reciprocal of the cosine. You notice I didn't do inverse secant. That'd be too confusing because we didn't go there. That's not one we need to work with a lot. So let's draw a picture, and let's prove to ourselves, then hopefully this will be kind of an oh duh. Draw me a picture where the cosine of theta is 3x over 5. Where's the 3x go?
Bottom.
Bottom? Where's
5
the 5
minus is
go?
5.
Diagonal. So the vertical is 5, well, 25 minus.
Now I want the secant of this. If the cosine was this over this, doesn't matter what that is, the secant's this over this. So is that one a gimme in a sense?
Yes.
Yeah. Yeah, always recognize a gimme because you realize there was something going on in it. Is it always going to look like that? No, but every now and then it will. And I just want to recognize it. I don't want to make that harder than I need to. All right, let's keep going. Let's do another secant, but let's do it of something else. How about it? Let's do the secant of the inverse tangent of, how about 3/4 x squared?
Oh, yay.
By the way, are there any restrictions on x? Every now and then, for example,
Oh,
can I have restrictions every now and then? Yeah, sure. Sure.
no.
Can I have restrictions on, yeah, because inverse sine can only be of numbers between -1 and 1. Yeah, so sometimes there are restrictions. Inverse tan, we said of any real number will produce an angle. So is there any restriction on that x? Can that, this is the ratio. Can this ratio ever be negative? So what quadrant are we in? We have to be in the first quadrant. If x is 0, we're on the x-axis. That's kind of boring. X can be 0, but even if x was negative, isn't this quantity here positive? So I have inverse tan of a positive number that produces a first quadrant angle. So the secant of that angle, my answer has to be a positive number. It's going to be. We're not going to mess with it. All right? So if that's my theta, and I always like doing it like this, just so I have no possibility of misinterpreting. Where do I want the x squared?
On top.
Yeah, it makes it a little easier. You're only doing this for the purposes of drawing a triangle that's representative. All right.
The
what
right
goes
is
where?
3x squared. The bottom is 4. The hypotenuse is root 9x to the 4th minus 16.
Everybody okay with that?
Yeah.
That's it? That's a yes? Okay. Cosine is this over this.
So secant hypotenuse
Secant is
over
this over
adjacent.
this. And because my denominator is a constant, it's actually easier to work with if I just write it as a coefficient. Because I might have to take a derivative of that. Now, is that correct?
Wouldn't that be 9x to the 4th?
Did I? Oh,
Yeah.
I thought you. I'm listening to you.
Yeah.
I think you said x squared.
Did I?
Pretty sure you did.
No.
Okay. Can that quantity ever be negative?
No.
No. So we have a consistency here. We said our answer could not be negative. Okay. You guys like this? It's not that bad. Well, this is going to set us up next day for exactly what we need, which is being able to take the derivatives. And the way we're going to do the derivatives of the inverse trig functions is not using limits. We're going to do them implicitly, just like we did the logarithm. And you're going to find out that that is just, it's not that hard. It's going to be really, really clean. Now, in the end, we're going to have 20 plus derivative formulas, and we're well over halfway there. We still have quite a few more that we're going to be doing over the next 2 to 3 weeks. So let me tell you what's going on now. We're still going forward. We still got stuff going on next day. We're going to do all of our inverse trig derivatives, but we're also going to build in some review into the class. This is where I'm going to go over, bring up the practice test key. We're going to go over, make sure everybody understands the nature of the test, what you can bring to the test, the way the problems are going to look on the test, everything about the structure. I'm going to explain everything. Like in some cases, I'm going to give you more problems than you have to do. You're actually going to have opportunities to choose. Let's see. Yeah, it's pretty straightforward. If you have any special circumstances that you're not going to be able to take the test at 11 o'clock on Friday, I need to know today so we can work out the logistics. I haven't had anybody ask to take the test on Wednesday. I think you could, but I think you'd probably be better waiting till Thursday. Right now, show of hands, how many are probably taking it on Thursday? Okay, I would encourage you, if you feel ready. If you're not ready Thursday, are you going to be ready Friday morning? Realistically? It means you're spending the night before preparing. That's probably not, You really want to come to class Wednesday saying, I'm ready to take the test, and if anything, I got to tie up a few loose ends. But I still need to go over major things. You can't have major things the day before a test, especially when we finished last week, right? So we've had time. It is absolutely essential that you've gone through the practice test before Wednesday's class. Otherwise, you're attending a review not having looked at any of the questions. No, the questions you're asking are not, can you do problem 1? Well, I have a detailed key, and that's exactly how I'm going to do problem 1. That's how I want you to do problem 1, and you're going to have me do it with the key right in front of you. Nothing's going to change. No, it's why did you do it that way? How would I have known to do it that way? How do I know what to do next when I start it that way? Pick apart a problem, but to say, can you do that problem? You already have a detailed key. That's not the question. Do I understand? You already have the answer of how to do the problem, but it's how would I have known? Could I have done it this way? What if? My favorite questions always begin with what if. Now I'm starting to think even bigger. And so we'll go over exactly the bounds. You know what's going to be on there. It's the first 8 lectures, so it's the first 8 quizzes. The quiz you turn in next day is the last material that potentially can be on the test. Obviously, nothing we did today and nothing we're doing on Wednesday, that's exam 2 material. Yeah, we'll cover all bases. Please do not leave Wednesday with unanswered questions. Ask every question you can think of, because every time somebody asks a question, we know that everybody benefits. Because everybody hears that answer and says, either, oh, I was thinking of the same thing, or better, you haven't got there yet, but you were going to think of that thing. Okay? All right, can you go ahead and stop recording? I'm going to do the roll. Okay, so today we are now starting new material that will be towards exam 2. So today and Wednesday is the next round of stuff. Today and Wednesday you're turning in the last quizzes that the exam will be made up of. So Wednesday's class we will do some reviewing for the exam. And the exam is on Friday. Several of you have indicated that you want to take your exam Thursday morning. Absolutely fine, doesn't make any difference. I want to make sure, though, if you're not going to take the exam on Friday, don't leave today without double checking and reaffirming, and so I want to get all the logistics correct. I don't want anybody kind of dangling in the wind. Different little scenarios. We will review on Wednesday, and so technically any time after that is certainly fair game, although I don't think any of you wants to take an exam minutes after class on Wednesday. I think that would not be in your best interest. I think you still want that little extra time to, double check, go over the last few things. Remember, the exam covers the material we finished last week, so you still have way over a week of preparation. Now today we're going to do something that it's a little bit different, and at first it doesn't seem like it has a lot of application, yet it really, really does. So I'm going to ask you a question. If everyone can pull out their calculators right now, everyone who has a calculator, you guys know what factorials are, right?
Yeah.
So if I asked you to do, let's say, 10 factorial on your calculator. So tell me what you get.
3,628,800.
Okay. If I asked you to do, let's say, 30 factorial on your calculator, now all of a sudden your screen looks a bit different now, doesn't it? It's giving you kind of a weird looking answer. What does it look like now?
2.652525859 times 10 to the 32.
Yeah, it gave you a scientific notation answer. How come?
That's too big.
Because it's too big. Yeah, that means this thing's 32 digits long, and nobody has a calculator screen that's going to show, I don't know, maybe you do, you wrap around. Is it practical to have all 32 digits, or is that more useful, just knowing it's on the order of 10 to the 32nd? But that's huge. Factorials are the fastest growing things that we have. In Calc 2, you're going to spend a significant amount of time working with these. Now, how about 69 factorial?
1.7112245 times 10 to the 98.
Now, one thing we do know about factorials. If I said 10 factorial, does that equal 10 times 9 factorial? Is that true?
Yeah.
And, just for fun, 10 times 9 times 8. These are ways I could do it if I didn't have a good calculator. So 70 factorial is obviously 70 times 69 factorial. So it's 70 times that first number, which is about, 70 times this number here is about 120. So that would make this approximately 1.2 times 10 to the 100. So just for fun, do 70 factorial on your calculator.
I received them.
And your calculator says probably what?
Overflow error.
Overflow error. Did you do something wrong? It gave you this one, but it didn't give you this one. What do you suppose the overflow error is? Well, I have a TI 89 titanium. I can go up to 449 factorial on mine, because that'll go up to 10 to the 999th power, and then it craps out and says overflow error. It said overflow error because your calculator won't store anything bigger than 10 to the 99th power, and this is now on the order of 10 to the 100th. Would you say that's a big number?
Yes.
Would you say 70 is a big number compared to infinities? No. 70 is pretty wimpy. What if you needed 1,000 factorial? What if you needed 1,000,000 factorial? What if you needed an astronomical large number factorial? There's no technology on planet Earth that can do that. The numbers are too big. But what if I actually need a value? You see where 70 factorial is not a very big number, yet our calculators can't even handle that. But what if, just for fun, how many here have ever written any computer code? We got a problem?
They're trying to figure out how to find factorial on calculators.
Yeah, you gotta go to the math menu and then all that kind of stuff. Don't worry about that now. I'm giving you an example, okay? if I use logarithms, don't we know this is true?
Yes.
So what if I actually needed a value? I really did need a value, and it was bigger than my calculator could do. Turns out I could use logarithms to help me get it. This is exactly how it's done. This is exactly how a computer will do it when the number is large. So if I wanted to do, I'll just do a small one, like 5 factorial. If I said I want the logarithm of 5 factorial, well, isn't that the log of 5 times 4 times 3 times 2 times 1?
Yes.
But the log of a product is the sum of the logs. Now do that for me on your calculator. Add up those numbers. The last one, by the way, is 0. So add those numbers. It's a really cool application of logarithms that we're going to show today. It doesn't even necessarily have to involve calculus. So when you added up these numbers, what do you see on your screen?
0.897.
So Mickey decimal. Now, I want 5 factorial. So I'm going to need to go e raised to this power, aren't I? Tell me, is this true? We saw this last day. Is this true?
Yes.
Yes.
So you have a number on your screen. I want you to do this. Go e raised to, and my favorite key is the answer key. The answer key is whatever you had on your screen a moment ago. Go e raised to the answer key. And what do you get?
7.
120.
Should get exactly 120. Should get exactly 120 because you just did e to this, you got back 5 factorial, which is 120. So what if I wanted to do a really large factorial? Now I said, how many have ever written any basic computer code? Anything, a do loop. You understand a do loop. For I equal 1 to 1,000 do. Add log I. So you add log 1 plus log 2 plus log 3 plus log 4 all the way up to log 1,000. You're essentially finding the log of 1,000 factorial, which means you just found the exponent. So no matter what your exponent is, your final answer would be e raised to that power, and all computers could store that because exponents aren't big. E raised to the exponent is a big thing. Now think about that for a moment. So if I wanted to do, just for fun, biggest number I know of is a bazillion. That's the biggest number there is, I'm pretty sure. I want to do a bazillion factorial. So it's a bazillion times a bazillion minus 1 times a bazillion minus 2, on and on and on and on, 3, 2, 1. Well, if bazillion is bigger than 69, I probably can't even do it on my calculator, but I want to do it for an astronomically large number. So what I do is I get my basic do loop. I don't do this by hand. Are you crazy? I did this by hand because I had to do 1 to 5. What if we wanted to do 1 to 100? Would we do that by hand? No, we'd write a simple computer program. That's what people do. So if I wanted the log of this, then based on what I just said, it would be each number added. So it would be the log of bazillion plus the log of bazillion minus 1, which is still pretty darn big, by the way. And how many times would I do this?
Bazillion times.
Dot, 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 down to log 3 plus log 2 plus log 1. This is a constant. Do you agree? And by the way, because it's an exponent, it's not nearly as big as you think it would be. Just for fun, let's take a big number. Give me a big number, huge number.
Million.
A million, okay. A million is pretty darn big. We all agree. Now, take the log of a million. What does your calculator say? Do the log of a million.
13.81551.
13.8 something?
Yeah.
That all of a sudden is not so big and scary, is it? That's kind of wimpy. Well, I'm a billion, a trillion, a bazillion. No, that number's not very big. Not the log of it. Because you're telling me the exponent. Oh, so if I raised e to this power, I get back the million. So let's give this an answer. Let's just call this number, I don't know, how about A for awesome? You did this not by hand. You wrote a computer program to just say for I equal 1 to a bazillion do, add log 1 plus log 2 plus log 3 plus log 4. I don't care how big that number is. If you do this on a computer, this is taking seconds, isn't it? This is not taking hours. This is taking seconds. Now you have some really, really big number in front of you. Can you now tell me the value of bazillion factorial? Yeah, it's e raised to this power. Isn't that what we just did here? Isn't that crazy? But at the same time, isn't that absolutely cool? You can calculate astronomically large numbers that are beyond what any human being can ever do with any technology 1,000 years from today. This is so far beyond the limit. The limits of technology are actually pretty weak. The supercomputer at UCSD can't even talk about 1,000 factorial, let alone. But that 1,000 is not a big number unless we do something like this. Now I can go as big as you want. But I'm using logarithms kind of to get me there. I'm using the fact that logarithms have these properties that the log of a product is the sum of the logs. Now what I want to do is employ this in some of the calculus that we already know. Not the logs we did last day, but actually stuff we did before then. And so I'm going to introduce something to you called logarithmic differentiation. Now, essentially what this means is I have something that does not involve logarithms. There's no logarithms in the statement. Last day we learned how to differentiate things involving logarithms, and there's some really simple and really cool rules. I want to talk about things that don't have anything to do with logarithms today, and I want to introduce logarithms as the way of making the problem work. So let me start with something really simple. Okay, let's start with, let's suppose y equals f of x. And I want to find dy dx. Well, we know what the answer is. It's going to be f prime of x. But I want to do it using logarithms. I'm going to show you a really roundabout way. This is not efficient. It's just another way of looking at it. So the first thing we're going to do is we're going to take the natural log of both sides. Okay? So now I can say with certainty that the natural log of y equals the natural log of f of x, as long as this is positive. Now I want to differentiate both sides with respect to x, so y is a function. So if I differentiate both sides with respect to x, we write it this way. We say d dx both sides. So in English, that means differentiate both sides with respect to x. So I'm going to go d dx of log y equals d dx of log f of x. Now, we learned last day the derivative of the log of a function is 1 over the function times the derivative of the function. And so the derivative would simply be dy dx. That's the left side. The right side, well, same thing. 1 over the function times the derivative of the function. Okay? Now, I wanted to know what is dy dx. I have this extra term floating around over here. So could I multiply both sides of this by y?
Yes.
Mm-hmm.
Would that be a legal move?
Yes.
Yeah. If I multiply both sides by y, now I have dy dx equals y times 1 over f of x times f prime of x. Which makes it really nice because how did we start the problem? Is that the result we needed to get in the first place? These guys cancel because they're the same thing. Now, was this the most roundabout way of ever taking a simple derivative? Yes, it was. But if I do this, it turns out there's a lot of problems that could be really complicated that we might be able to make really simple. Now, I'm going to start with something really simple, like product rule. I'm going to revisit product rule. Now, we don't have any question on product rule, and in general, that's not something that's going to usually give us much of an issue. Y equals, let's say, we'll keep it simple, f of x times g of x. All right? That's what y equals. We can put anything in there we want. I want to use the logarithmic differentiation, which means there's no logarithm associated with the question. I'm going to take the log of both sides and then differentiate that new problem. And when I do that, I want to show you the steps along the way, because then we're going to do it for several different types of things. First thing we're going to do is take the log of both sides. Now, look at the right side for a moment. Can I do anything with that?
Yeah,
What can I do very specifically?
the product of logs is equal to the sum of the logs.
The log of the product
Oh, the log of the product.
is equal to the sum of the logs. So is it true that this is log of f of x plus log of g of x?
Yes.
Now, what's easier to take the derivative of? F of x or f of x times g of x? Well, just f of x, right? Differentiating a product is always way more work, but I don't have to differentiate a product anymore on the right side. Huh. All right, let's take the derivative of both sides. So on the left, just like we did before, I'm going to get 1 over y times dy dx. On the right-hand side, I'm going to get 1 over f of x times f prime of x. Can I be lazy and just put f prime in the numerator?
Yeah.
Yeah. Does anyone have a problem with that? See, I didn't do it here. I could have just put that in the numerator, couldn't I? And it probably reads a little easier. And what's the next term?
G prime x over g of x.
So far, so good. Now, I have a sum of two things. I really would rather that look like one quotient. I think it would be easier to work with later. How do I make that into one quotient? I need an orange pen to do that. Here we go. Well, let's see. Could I multiply by g of x over g of x here and f of x over f of x here? Is that legal if I do that?
Yeah.
Yeah.
Okay. Then on the right side, I would now have g of x f prime of x plus f of x g prime of x all over f of x times g prime of x. Okay. Now, I want dy dx all by itself. For me to get dy dx all by itself, I need to multiply both sides by y. Agreed? So it'd be y times all of this stuff. All right. Oh, by the way, what does y equal?
That.
Are these going to cancel? Yes? No? Maybe?
Yeah.
Oh, and what am I left with?
Product.
That looks like the product rule to me. Huh. Well, it would have been way faster just doing the product rule. You're right. You're right, it would have. This time. I think you're going to like this one a little bit better. Remember doing this one? I think this was on your quiz you just got back. Didn't we have a problem like this? We found the derivative?
Yes.
There was a lot of algebra. It wasn't hard algebra, but we agreed there was a lot of algebra.
Yes.
What if I do the logarithmic thing on this one? I'll just write it like this. Now, why would I do such a crazy thing? Well, the first thing, this is log of a product, so that's going to be so far so good. Oh, but it gets better. Abominable snowman, you guys see him?
Mm-hmm.
Remember, he lives in the exponent. What's he gonna do?
Bounce.
And his buddy? Huh. So now the right side is 3 log of something simple plus 4 log of something simple. And all of this, by the way, is equal to the log of y. I haven't done any calculus yet. I haven't taken a single derivative. I took the log of both sides and then I used log properties to simplify the right side. Now let's take a derivative. So when I differentiate the left side, it's going to be 1 over y dy dx. What's the right side going to be? Okay, this part I know. Is everybody okay with this? Those guys are going in the denominator. I have no question about that. So what goes in the numerator? What goes in the numerator here? What's the derivative of 4x minus 2? 4. What do I do with the 3? Oh, okay, how about 3 times 4? What's going in the numerator here? 6. But I had the 4, so. I am completely finished with the calculus for this problem. There's no more derivatives. Now, I would prefer this be one quotient. I think it would be easier if I wrote this as one quotient. So in order for me to write this as one quotient, I need a common denominator first. So let's see, I think I need a 6x plus 3 over 6x plus 3 here. And here I think I need a 4x minus 2 over a 4x minus 2. Are we good on that?
Yeah.
Let's go ahead and distribute and gather terms. I think that's not too bad. So I have 12 times 6x plus 3, that would be 72x plus 36. Then I have 24 times 4x minus 2, I think that would be 96x minus 48. Okay, a little higher. So it looks like I have 168x minus 12 over this. Okay. And what does all that equal? That all equals 1 over y times dy dx. So just like before, I would like to say dy dx equals. So dy dx is going to equal that. Actually, give us a little more space. Multiplied by y. Agreed? But rather than write y, why don't I just take the original problem, which was that? Because that's what I'm going to end up doing anyway, right? I'm going to put that in there. So if I put that in there, then I have 4x minus 2, 6x plus 3 to the third and fourth powers. All right. I'm done, right? Well, can I do a little canceling? What's going to cancel? Would you say all but one of them? How about here? All but one of them? Oh, that's it. Sorry. And that's exactly the answer we would have gotten if we had done it the way we did it before, using the chain rule, factoring, gathering all the terms and all that kind of stuff. Same answer. But the algebra on this one was probably a lot less, wasn't it? Huh. Interesting problem. I got one more for you. You're gonna like this one. We're pretty good with product rule. I think as a group, product rule is not something we're going to labor over. I think product rule is something we're not going to labor. Okay, what did I just do? I want the derivative of this. How would I do that? By the way, I can keep going. I can put more. How do I take the derivative of 3 functions in a product? Is it still product rule? What do you think? Would it still be product rule? Yeah, but what's my first function and what's my second function? So maybe we do something like this. Maybe we call f of x my first function, and we call g times h my second. Would that work?
Yeah.
Is this gonna be a bit of work?
Yeah.
Oh, yes, it is. So I'd say first times derivative of second, and then I gotta use product rule in there. Second derivative of first. You agree that this one could be a little bit huge? Now, in theory, I didn't technically have to put these over a common denominator. We did because we wanted our answer in a factored form. I want to do the same problem, but I don't really want to do product rule multiple times. Oh, by the way, if you're okay with doing 3 functions, then let's do like 7 functions or 15 functions in a product. You got time, right? You got no plans for the rest of the year. What if I use logarithmic differentiation? You're gonna like this because this is the reason we learn it, is for stuff like this. What if I do this? Now tell me about my right side. I have log of f times g times h. Isn't that log of f plus log of g plus log of h?
Yeah.
Are these individual derivatives more or less difficult than the original problem?
Less.
A lot less. I'm only differentiating one thing at a time. So when I differentiate both sides, I d dx both sides. There's my left side, like always. But what's my right side? What goes here? F prime. Here, g prime. Here, h prime. And I'm completely finished with the calculus. Did I use any product rules here? No? Ooh. So, what is dy dx? It's y times all of this. Correct? But what's y? Y was f times g times h. Could I have done this for more than 3 functions, by the way?
Yeah.
Is what I'm doing more difficult with more functions, or is it the same?
Not really.
If I added 10 more functions, you just keep going, but it's not harder, I just got more stuff. But the next thing we write will be the final answer to the problem, whether we had 3 functions or 3,000 functions. If you were differentiating 3 or more functions in a product, you would always want to do the logarithmic. I'm telling you, it'd be significantly easier and faster. When I distribute, what am I going to be left with? G H F prime plus F H G prime plus F G H prime. I'm done. That is the 3-way. If I do 3 functions. What if I had a 4th or a 5th or a 6th or a 7th? You can kind of see an algorithm. No, you're never going to have to worry about that. Don't worry. In this class. Can that happen in other levels, in physics and other? Yeah. And the thing is you have a technique. I don't want to call it a trick. It's a very specific technique that I take a problem that did not have logarithms. I use the properties of logarithms, namely the log of a product is the sum of the logs, or the log of a quotient is the difference of the logs. And I use that to my advantage. Now, does that mean the problem is going to be easy? No, but it's very likely to be less work and certainly less algebra. Now, we did problems of this nature a few lectures ago. Do you remember what the worst one was, though? I think we had a quotient and we had roots. Ugh. I don't want the answer so much as the setup. Let's do one more really terrible one. So how about y equals, how about the square root of 6x cubed minus 4x squared over, I don't know, let's say the cube root of 2x to the 6 minus 6x cubed, and I'm raising that to the 4th power. I don't know, that's pretty hateful. Do we agree this is horrible?
Yeah.
Good, okay, good. I want the derivative. But let's set it up that way. So if I do the log of y, then it's the log of all of this big gobbledygook, right? How about if I rewrite the bottom as 2x to the 6th minus 6x cubed to what power?
Some 4/3.
To the positive 4/3? And what would I write the top as?
To the 1/2.
To the 1/2. The log of a quotient in English is the
Difference of the logs.
difference of the logs. I'm not going to skip any steps because I don't want anybody to get lost. I think we all agree the original problem was downright scary. Now, what can I do with those exponents? Right? You all know the sound they make. Have we done any calculus yet?
Nope.
No. But we're going to take the derivatives of these two guys. This is the only calculus step in the problem. Now I'm going to differentiate both sides of this with respect to x. So this is not log of a variable, this is log of a function. So it's 1 over the function times the derivative of the function. That's why we write it like this. And on the right side, that's, sorry, cube. Okay, and then now that 1/2, I'll just put it right here. That 4/3, I'll just put it right here. What goes in the numerator here?
18x squared minus 8x.
18x squared minus 8x. What goes in the numerator here?
12x 5. And 6x squared.
Can I distribute both of these fractions into the numerator? I think I can in both cases. So why don't we do that? Then we get rid of the fractions. So now that would be 9x squared minus 4x over nasty stuff minus, what would that be? 16x to the 5th minus 8x squared. Now this is 1 over y dy dx.
I think your 2's at the very end of your equation are supposed to be 6's. This would be 6x.
Oh, hold on a second. Where are we?
So
Did
the
I?
bottom
You're
equation,
right.
yeah.
You're right.
So then,
Ah.
those are both supposed to be 6.
That's supposed to be a 6. Thank you. So
And so there's a.
where does that
top would
one
be-
come in? That comes in.
It'd be 18x squared.
Good catch. Good catch. That's a 6, so that's an 18. Good. Okay. And then that makes that 24. Now we want to get it right. Thank you. Now, this is 1 over y dy dx. What does y equal? I'm sorry. Sorry. What does dy dx equal? I'm going to multiply both sides by y. How do I want to represent y? Do I want it with roots or fractional exponents, do you think? What would be easier, do you think?
Fractional.
Probably fractional exponents. So that would be 6x cubed minus 4x squared to the 1/2. And if I write it times, that's not going to hurt anything. 2x to the 6th minus 6x cubed. To the negative 4/3. Now, when I distribute here, when I distribute this into here, this is one of them is going to cancel with this guy. And when I distribute this into here, something's going to cancel with this guy, and I'm done. Now, there's still some factoring, there's still some common denominators if you choose. But if we go back and look at how we did this problem last day, that was pretty big and scary. But where did I use the fractional exponents in this problem? I didn't. They became coefficients of the logarithms. So one of the huge benefits to logarithmic differentiation, again, is it takes exponents kind of out of the picture, especially when I have functions raised to powers. Do you ever have to use this as a method of doing a problem? No, but there are many times it will make the problem way simpler, way simpler. Okay, I'm going to give you an example of one right now. All righty. Last day we did some implicit differentiation problems involving exponentials and things, and could get kind of hairy at times. So what if we have something like this? I've got, how about e to the y minus y squared e to the x, I don't know, equals, how about 3? And I want to find dy dx. Well, the way we did this last day, we did this implicitly. And this isn't the worst problem in the world. They're way worse than this. So I'm going to differentiate both sides with respect to x. The derivative of e to the y with respect to x. It's e to the thing, so its derivative is e to the thing
dy dx.
times derivative of thing, which would be dy dx, exactly. Minus first times derivative of second, plus second times derivative of first, which would be
2y dy dx.
Do you notice how I kept the negative on the outside because both terms are going to be negative? What's on the right side?
0.
0. I like that. Big fan. Okay? So I'm going to remove the parentheses. And when I do so, what happens to the sign?
Changes.
That's going to become a minus. So it looks like I need to send that guy back. So on the left side, I now have e to the y minus 2y e to the x, all dy dx. And that's going to equal y squared e to the x. So when all is said and done, dy dx equals y squared e to the x, e to the y minus 2y e to the x. That was busy. That was a lot of work. Can I improve upon this at all?
You could factor
Is it possible to write this answer without even having an e in it? Well, let's go back to the very beginning of the problem. What does e to the y equal? Wouldn't it equal 3 plus y squared e to the x?
yes.
Could I replace e to the y with that? Would that be legal?
Yeah.
Well, if I did, this would now be y squared e to the x, and this would be what?
3 plus y squared e to the x
Minus 2y e to the x. I might be able to manipulate the e to the x's somehow or another. I don't know. Maybe it gets crazy, maybe it gets weird. Everything we said is true, everything we said is correct, and that's a perfectly good answer. What if we had tried logarithmic differentiation in this problem? And by the way, this is the kind of problem you really want to, because what's the log of an exponential function? Just the exponent. What if we had done this problem in that way? I know people in general aren't always comfortable. You know, I'm gonna make one small change in this problem. I'm gonna make one small change for the next thing I'm gonna do. I'm gonna do the same problem, but instead of a 3 on this side, I'm gonna have this just be a 0. By the way, the derivative is still the same because there's no 3 in the answer. I'm gonna make that a 0. So then I can say that this is true. Okay? So I've got, the original problem was this. So I'm gonna write it like this. And now I wanna do the log of both sides. And the only reason I wanna do the log of both sides is because I have exponential functions on both sides. And the log of the exponential function is just the exponent. Okay, it might make the whole problem a little easier to look at. So what have I got on the left now? No calculus yet, I just want, what's the natural log of e to the y? Because. Oh, you meant the very, yeah. Terrible, terrible human. Okay, log of the product?
Sum of the logs.
And can I,
2 on the y.
This is the original problem, this is the exact same problem. That doesn't look as scary, does it? There's no exponential things. So now let's differentiate both sides of this thing. So if I differentiate both sides now, and by the way, I'm not introducing new logarithms, I've already introduced the logarithms, they're right here. This is the only place where it ended up showing up. So on the left side, I just have dy dx. On the right side, I'm going to have equals 2 times 1 over y times dy dx. And the derivative of x is just 1. I have 2 different terms with the dy dx in them. So I'll send this one this way. So now I'll have 1 minus 2 over y, all dy dx. On the right side, I have just a 1. Now I need to multiply both sides by the reciprocal of this. I don't like that yet. Let's make that into one quotient. It'll be a little easier to work with, right? Because there's my 2 over y, there's my 1. If I make that into one quotient, what will it be?
Y minus 2 on top?
Just y minus 2, yeah. So now I'm going to multiply both sides by the reciprocal of that. So when all is said and done, dy dx is simply y over y minus 2. There's no exponential in my final answer. By using logarithmic differentiation, I ended up being able to whittle this thing down so much simpler than it would have been otherwise. That's a much easier version of the answer, isn't it? So logarithmic differentiation means you didn't start off with logarithms. If I give you logarithms and say do the derivatives, you just do them. We have straight up formulas. We have a problem that does not involve logarithms, but by taking the log of both sides of the equation, I might end up making a simpler problem as a result. Maybe, maybe. Now let me give you an example of one. This one comes up a lot. We derived a formula for this last day. I did the e to the log thing and we manipulated that. You're doing homework, you're out and about, you're wherever you are, you have terrible cell phone reception, you need a formula, you don't have one at your disposal, but you still need to take this derivative. And you can't remember the formula. Oh, darn. Is there an easy way to derive the formula? How about if I do this? Then what does this become? Is that true?
Yeah.
So when I differentiate both sides, what's the derivative of x times a constant?
Constant.
The constant. So dy dx is equal to y times the constant, or a to the x log a. Isn't that the formula we derived? Yeah. But if you couldn't remember it, could you get it this way? Yeah. And it's actually really convenient. In fact, this is kind of funny. Here's an exam question. Here's an exam question. I want you to, sorry, let's write this way. All right, I have 10 to the x. I want you to find the derivative. Well, we have a straight up formula, but you can't remember the formula. So you use logarithmic differentiation. And then you're going to get that as the answer. I don't care how you got that as the answer, as long as you get that as the answer. Now, we have a formula, we have the answer in the next step. But you can't remember the formula, so you did the logarithmic differentiation to derive it. Is that still valid? Oh yeah, it's not entirely practical, but it is still valid. So anytime you have something involving exponents, in general, logarithmic differentiation often will make it faster. I can't say it will always make it faster, but it will often make it faster. If no exponents are involved, but I have a product, like product rule, then it might be an advantage. But if you just had one simple polynomial, there's no advantage to doing a logarithm. But if I have products or I have exponents, then I can use properties of logarithms. The same thing is true with quotients. You don't suppose we could derive the quotient rule using this, do you? You remember how we derived it using the chain rule the other day? I derived the quotient rule by only using chain rule. Well, this ought to be interesting, just for fun, because again, that's our primary goal in this class. I've got a quotient of functions. And I'm completely blanking out on quotient rule. But I got this logarithmic stuff nailed. I know that would be weird, but could happen. So I want to do the log of both sides. Now I have to be careful when I rewrite the right side. I got to have the rule correctly. The log of a quotient is the difference of the logs. Okay, I haven't done any calculus yet. Now I want to differentiate both sides with respect to x. So the left side will be 1 over y dy dx. The right side will be, I'll write it like this to remind us. 1 over f times f prime, so I'm just going to put the f prime here, it's easier. I'm done with the calculus. But it's probably easier if we write this as one quotient. So if I put this as one quotient, then I'm going to go g over g, f over f, okay, that's 1 over y dy dx. So finally, I can say that dy dx is that stuff that I have right there. I'll rewrite it. Times y. What was y? Y was f over g. Does anything cancel? And I'll have a new denominator that has a g squared. And what will my numerator look like?
Quotient rule.
Ho d high minus high d ho. Is that the quotient rule exactly? Yeah. A little easier than limits, huh? In fact, it might even be easier than using the chain rule. One of the beauties about calculus is it's so internally consistent. No matter how many ways we can look at a problem, we always get the same answer if we did it right. I don't need anybody to rederive the quotient rule. But isn't it nice that this thing that we're learning absolutely confirms I'm still getting the same answer? Remembering the quotient rule is more practical. So logarithmic differentiation is a tool. That's all it is. You never actually have to use it, but if you have it in your tool belt, sometimes it makes problems easier. And I say that in all seriousness, that you have a lot of tools and some of them are dormant, you don't use them. If I had a quotient of polynomials and the degree of the numerator were greater than the degree of the denominator, I have to perform the division. So whether it's a synthetic division or a long division is not the important thing, is that I have to do it correctly. But if I know both synthetic and long, then I perhaps can choose depending on the nature of the problem. If my denominator were linear, I would go synthetic. It's easier, it's faster. But if I don't have that in my tool belt anymore because I've just forgotten it, too much rust, I can still get there using long division. It'll take me longer. I would always opt for the fastest way to do every problem. But that comes with experience and lots of practice. Okay? All right. Oh, there's my briefcase. Let's go ahead and stop now. I need to do the roll thing. We're gonna do some Trig-ish stuff now. Gonna go into our Wayback Machines and look at some things. So I wanna go even further back. And we want to talk about, just for a moment, inverse functions in general. Some of the rules and regulations. Now, if you can write anything, an equation at all, it has, I'm talking about from a graphing standpoint, x and y, it's going to have an inverse. But inverses are not always functions. So let's start with a really simple one. If I started with y equal x squared, now we know what that looks like. That's pretty easy, right? It's a simple parabola, because that's a terrible parabola. Let me do this one more time. That's my next one, not this one. I want to do y equal x squared. Let me go way up high. Okay. And then its inverse would be x equal y squared. I'll use a different color, which would be this one. Anything that you can write down to get the inverse, all you do is swap the roles of x and y. Because the definition of the inverse is input becomes output, output becomes input. We all agree that the parabola y equal x squared is a function. But is the parabola x equal y squared a function? Why not? Yeah, because I have many, many, many x values that give me different outputs. Right? And that violates the function. A function, each input has a unique output. And the sideways parabola is not the case. So why did that fail? Well, let's draw another graph. What if I have a graph, and let's keep it really simple, something like y equal x cubed. This is a nice, happy graph. Well, if I swap the roles of x and y, I have the cube root function, which essentially looks like this. Okay, so this is y equals cube root of x. This is y equal x cubed. Is the cube root function, is the cube root a function?
Mm-hmm.
Yes.
So when I did y equal x squared, that's a function, but its inverse was not. Here, y equal x cubed is a function, and its inverse also is a function. Is there a big difference? Now, why did it fail? What were the words you used? It failed.
More than one y.
Yeah, but that's not the term. You said something about.
Vertical line.
Yeah, remember from kids in algebra. If it is possible for me to draw a vertical line that passes through more than one point, it's not a function. Because that means one input gives me multiple outputs. But y equal x squared is fine. Its inverse failed the vertical line test because the original function failed a horizontal line test. A horizontal line test isn't a test to see whether something's a function, it's something else. It's a test to see whether something's what's called one-to-one, and that's the key. Some of you may remember that term. One-to-one. Okay, first of all, we're starting with a function. That means each input has a unique output. One-to-one means each output comes from a unique input. If I go to the number 9 here, aren't there two different inputs that gave me the number 9?
Yes.
If I input a 3 or a -3, I get a 9. So although it is a function, each output did not necessarily come from a unique input. It didn't work in reverse. In other words, I can't go backwards. What number when I squared is 9? You have two possibilities. I'd really rather only have one. So if my function fails a horizontal line test, then its inverse will fail the vertical line test. Everything has an inverse, not every inverse is a function. Did the cubic graph pass a horizontal line test?
Mm-hmm.
Yes, and so therefore its inverse passed the vertical, because all I'm doing is flipping basically over the line y equal x. So if a function is one-to-one, then we say the function is monotonic. You want to take a stab at what that might mean? Well, what's mono? One. Monotonic. It's always going uphill or it's always going downhill means it's going in one direction. That's it. A monotonic function is always going uphill or it's always going downhill. It does not turn around. So a function has to be monotonic in order for the inverse to also be a function. That's absolute across the board. So what if your function's not monotonic? Then how in the world do I find an inverse? Well, then we do something that, again, some of you may remember this. If I talk about y equal, I'll put it up here, y equal x squared, what is the domain and the range? Maybe I'll use it here. Y equal x squared only. What's the domain? All reals, and the range is?
Positive?
Zero.
How about 0 to infinity? Yeah, non-negative actually would be how we'd say it. Okay, now let's look at it at the inverse, which is x equal y squared. What's the domain of this one? This is an absolute across the board for everything that exists. When you do the inverse, tell me about your domain and range. Yeah. It's not an inverse if they don't just simply switch places. So you don't actually have to think, what's your domain? 0 to infinity, your range. By the way, if you did not learn this in remedial algebra, probably pre-algebra, somebody did you a disservice because you use this pre-algebra, elementary, intermediate, trig, pre-calculus. Inverse comes up in every one of those classes and it gets bigger and bolder in each one. You do the inverse trigs and trig and you do inverse of everything else in pre-calc. But this is an important one. We need to know this one. Domain and range simply switch places. Let's go back to here. Y equal x squared is not monotonic, but is maybe half of it monotonic? Which half do you want to, would you want to use? Maybe everything to the right of the origin? So just for the heck of it, I'm going to erase this, and I'm only going to use this, which means I'm only going to use this. This is what is called restricting the domain. I'm going to use less domain. Is the portion of the domain I used going to make this monotonic?
Yes.
Now, what's going to happen to my inverse when I do that?
It's going to exist.
It's going to be that, isn't it?
Yes.
When I restricted the domain of the original, then I'm also restricting the range of the new one. Now, by the way, when I restricted the domain, did I change the range at all?
No.
No. So it's very important that I restrict it in such a way that I don't lose any of my range. Now look at that picture. Is my original function now monotonic? Is its inverse now a function?
Yes.
And what is that inverse called?
F.
Very specifically? Square root function. Ooh, that's the square root function. When I take the square root of a number, I don't generally get two values back, do I? I just get the one. Oh, so the square root function is defined from the y equal x squared if I restrict the domain. So if I take something that's a function and I restrict the domain if I had to make it monotonic, then its inverse is automatically a function. So why am I doing that? Because now we need to do this for all of the trig functions, which you have done in your life. You just haven't done it, well, recently. Okay, so let's start with something. Let's start with y equals the sine function. My pens are all sort of dying here. All right. Do we agree this goes forever and ever in both directions?
Yes.
Okay. This is clearly a function. Is its inverse going to be a function? No, its inverse is going to zigzag along the y-axis. Here's the problem with this, okay? The sine of pi over 6 is equal to, this is a common one. Use your calculator if you want.
There were 2 over 3.
That's easier now.
This is 1 over 2.
Yeah, it's a half. Yeah. The common angles are good to know because they come up often. So if I were to draw a unit circle, let's say, I know that point is root 3 over 2 comma 1/2. I know that. So the cosine of that angle I know is root 3 over 2. That's, all right? So what's the answer? Is the answer pi over 6? Well, certainly that works. But what about pi over 6 plus 2 pi? What about pi over 6 plus 242 pi's? How many times can I go around the circle and end up there?
As many as you want.
As many times as I want. So how many different representations are there of this position? Infinitely many. They're called coterminal angles. Ooh, so I wouldn't say pi over 6. I'd say probably pi over 6 plus like 2k pi. While we're at it, isn't the sine of 5 pi over 6 also 1/2? Oh my God, there's not only infinitely many answers to this question, there's also 2 places on the circle I could be. You see the dilemma we have here. So, I really would like to get pi over 6 back again though. I would really like to ask the question in such a way that the only answer you gave me was pi over 6, not infinitely many coterminal angles. In other words, go back to the original parabola. The very fact that I got more than one answer when I asked what gave me this number, when we restricted the domain. Could I restrict the domain of the sine function?
Yeah.
Well, right now, do you agree that domain is all real numbers for the sine function?
Mm-hmm.
There's no restrictions on the domain, and right now, what is the range?
-1.
Is it -1 to 1 inclusive? So what I want to do is use, well, less of the number line without in any way messing with the range. I still need peak to peak, but I don't want to go back and forth. I don't want to turn around. So is there a portion I could choose that would cover all the y values without ever repeating anything? Yeah, maybe, I don't know, from about here to here? What do you think? And that's negative pi over 2. That's pi over 2. You notice I'm not saying 3 pi over 2. If I said what is this angle, we'd say 3 pi over 2. If I said backwards, we'd say negative pi over 2. They're both correct. But here, that's clearly negative, and that's clearly positive, because now I'm on the xy plane. So if I restrict the domain here to be just this, now when I ask for the inverse, will the inverse be a function? Yeah. And by the way, I don't need to know what the inverse looks like, but it's not very hard. I just take that graph and flip it. We're going to do this probably many times in calculus. So the inverse, I know what the sine wave looks like. The sine is doing that kind of thing, so the inverse is doing something like this. I have a horizontal tangent right here. So this should have a vertical tangent right here. This is my inverse. Well, in the case of y equal x squared, we said x equal y squared, but wouldn't it technically be y equals square root? Wasn't that its inverse? So I want to say y equals, not x equals. If y equals sine x, is it correct to say x equals sine y? Is that a correct statement mathematically? For here. Yeah, if I want the inverse. But I want the inverse to be a function. So this one, we write it like this. This is inverse sine. Anytime you have a -1 in an exponent position on a function, it always means inverse. In no context does it ever mean reciprocal. Ever. What's the only mistake people make? They use reciprocal, which means they get the wrong answer to every problem they will ever do the rest of their life when it's an inverse. An inverse is not a reciprocal. What's the inverse of a positive number? Is it its reciprocal? Is it its square root? Its square root's logarithm? It's negative sign? Well, it depends what the operation is. Oh. So if I'm adding, the inverse is the additive identity, which if I'm exponentiating, the inverse is the logarithm or the root, depending on which version I'm using. Inverse is not reciprocal unless you're multiplying. Do people say reciprocal? All the time. No, in no situation, this is an absolute mathematical statement right here. You will never run into anything where this is a true statement, ever, in your entire lifetime. So don't do that. Don't do that. That no work. This is called the inverse sign. Now, let's go back to here. When I'm doing the sine function, what am I inputting? Sine of pi over 6. What am I inputting? What is pi over 6? It's an angle. What am I outputting?
The coordinate.
Okay? Or you, simply the ratio of something. It's a ratio. On the unit circle, it's the coordinate divided by 1, but if I'm not, think so katoa. Right? Isn't it so? Opposite over hypotenuse? In other words, the sine function gives you back the ratio of two sides. On the unit circle, it's the coordinate versus 1, which is why the unit circle is really helpful. I input an angle, I output a ratio. So what am I going to input in here?
The ratio.
Ratio, and I'm going to output the angle. So get out your calculators. I want you to do the inverse sine of 1/2. By the way, to make it easier, the answer to any question of this nature is always a radian answer. But if your calculator's in radian mode, tell me the problem with your answer right off the bat. It might be correct, but what's your answer going to look like?
Long decimal.
A decimal approximation of pi over 6, which of course you all have the first 10 or 12 digits memorized on pi over 6, right? Everybody knows that one. Now, that's something you learned as kids, right? Or maybe no? Does any of you have fractional multiples of pi memorized in your head? So if I do this in radian mode, which is correct, I'm going to have an ugly decimal on my screen. How do I know if I did it right? Whenever you do an inverse trig function, do it in degree mode. And then change your answer to radians. So put your calculator in degree mode and do inverse sine of 1/2, and what does it say?
30.
30 degrees, which is pi over 6 radians. That's what I would do. Why? Because the answers are not always going to be common angles. But if the answer is a common angle, like 30 degrees, 30 degrees is pi over 6. That's an easy one. But what if it was, 37.3 degrees? Well, that's not a common angle. Then I'm not worried about it. Right now, it's just some icky decimal. So the inverse sine of this ratio produced exactly one angle, not all the coterminal angles, one angle. Which angle did it produce? The angle between here and here. So if I'm looking at a unit circle, inverse sine on the unit circle only produces angles on this side. First and fourth quadrants, but the fourth quadrant angles it produces are negative angles. So if I'm in the fourth quadrant, I'm not getting large angles, I'm getting small negative angles. Because again, going back to this picture, I'm getting negative to positive. So negative pi over 2 to positive pi over 2, okay? You have a calculator if you actually have to do the calculation, but understand what it is you're producing. Now, in general, we're not that concerned with inverse cosecants and inverse cotangents and inverse secants. We are concerned with inverse sines, cosines, and tangents because they come up a lot more. So let's do the same thing now with the cosine and the tangent function. Let's figure out where our restricted domain puts us. All right, so cosine function. Looks just like the sine function, only it's slid a bit. So it's almost the same graph, just slid over. So in this case, I need peak to peak. So I can certainly select this section or that section or that section or that section. This was easy. The peak to peak went right through the origin. That made my choice kind of a no-brainer. Do we want to include 0 in our answer? Probably. I mean, I don't want to go down here. Yeah. So should I include all the negatives or all positives? Do you think, to make our life easier? Probably the positives. So we agree. This is not some rule. We didn't solve a problem. We agree as a math community. We're going to take this portion because that will produce all the y values and it's monotonic. Well, that's pi. So if I take the cosine function and I restrict the domain to the closed interval 0 to pi, I'll still sweep out all the y values, but now I can define an inverse trig function that will produce one answer and one answer only. So this is how we determine the inverse cosine. So we do agree that the range here, just like the sine, is still -1 to 1. So now I want the inverse cosine of 1/2, let's say. So my calculator should produce an angle.
60 degrees.
60.
So in degrees it's 60 degrees, so in radians it would be
1/3 pi.
5/3. Say, well, that wasn't that hard. Does this come up a lot in math? It comes up. I don't know if anything comes up specifically a lot, but what we're doing is way beyond the ability to calculate a number. We're using this for much, much bigger purposes than this, but we're reminding ourselves the whole point of an inverse is to produce a function that gives us back one answer, not multiple answers. We don't like that, okay? We don't like multiple routes because that might not be the same thing then. You might get different values. And finally, let's consider the tangent function. Now the tangent one is a little bit weird. There's my tangent function. Well, sort of. Because there it is again. And there it is again. In fact, how many times does this show up?
Infinite.
Infinite. Oh, there's an infinite number of these guys, aren't there? Yikes. These are vertical asymptotes. That's at x equal pi over 2. That's at x equal -pi over 2. So the tangent function, actually, my choice now is pretty easy. This is going from way down there to way up there. It never turns around anyway, but it does repeat itself. So I'm going to use this one right here because it's the only one that passes through the origin. So if we restrict our domain from -pi over 2 to pi over 2, now it's open. If you do tangent of pi over 2 or tangent of 90 degrees on your calculator, it's going to say error because it's technically it's undefined. It's 1 divided by 0. I can do the tangent of 89.9999999 degrees. Right, and that's going to be very, very, very steep, but I can't do tangent of 90 degrees. So if I restrict the domain to this, tell me about the range of the tangent function. What's the range, you think?
All real.
So how about all reals? -infinity to positive infinity, exactly. All right, go back to inverse sine for a moment. Input inverse sine of 10. What does your calculator say?
Error,
Why does it say error?
because it's not a ratio.
Just it's an inverse sine of 10. The sine of what angle gives you 10?
Oh, see, I got a domain error too.
How come?
I don't know, there's a domain error.
Because didn't we say the sine function bounced between -1 and 1?
Yes.
Oh, so when I take the sine of an angle, can I get a value outside -1 to 1?
No.
Not really. Well, yeah, I can, but that's a couple weeks away. In other words, if I consider imaginary numbers and things. But I can't use a real number. There's no real answer to that question. There is a complex answer to that question. We're going to see that later. But basically, we agree that sine and cosine stay between -1 and 1. But the tangent can produce any real number. So if you do inverse tangent of any real number, you will get an answer back again. All right, so do the inverse tangent of 1. Start with an easy one. Inverse tan of 1.
45.
It's 45 degrees
Pi over
or
4.
pi over 4 radians. I would always use degree mode first, because then if it's a common angle, I can easily convert it to radians. But does anyone here recognize the decimal equivalent of pi over 4? Yeah, probably not. Right? That's not something you see. If you saw pi on your screen, is it likely you'd recognize it? It's likely you would recognize it. You know, okay, 3.14, so okay, yeah, that looks like pi. But any version of that, any multiple, any fraction of that, you're probably not going to recognize. That's why it's easier if you're in degree mode for the purposes of figuring out where you are, and then always take the degree answer and converting it back. So if I do the inverse tangent of any angle, I will get back, excuse me, any ratio, I'll get back an angle between -pi over 2 and pi over 2. That makes things very, very practical. So let's do an exercise. I'm going to go way back. I subbed for a trig class multiple times already this semester, And we were doing this on the third or fourth day of class already. So this is how early you started this process, all right? I'm gonna tell you that the sine of theta, use theta as my angle, is, let's say, 3/5. I want you to find for me, how about the cos theta, the tangent of theta, the secant of theta, the cotangent of theta, the cosecant of theta. Now, there's one other thing I need to tell you. What quadrant I'm in. Because the sine is positive in both the first and the second quadrants, but not all the other guys are. So, I want the sine of theta to be 3/5, and theta is in the second quadrant. Now, you guys have all done this. I'm going to walk you through how you did it again. You're going to go, oh, yeah. That one really didn't give me too much trouble. The best part about this, I never actually need to find the angle. Because my answer is not the angle, my answer is the cosine of the angle. So what I'm going to do is draw a picture, not a unit circle. You can always do a unit circle, but now you're dealing with icky quotients all over the place. I'll just draw a simple SOHCAHTOA picture. I'm in the second quadrant. There. Can you draw me a picture, that's your right angle, where the sine of this angle is 3/5?
The y would be 3.
Where's the 5?
The 5 would be the r, just the diagonal.
So what would this be? Would that be positive or negative?
Negative.
Negative. How would I find this value?
-4.
So in other words, you're saying negative, this is going to be negative something, comma 3. Well, if I use Pythagorean theorem, what's that other side?
-4.
Negative 4?
Yeah.
Whether you put the -4 here or you put -4 here, I don't really care. Is this triangle representative of the question? All right, can you tell me the answer to each of these without doing a whole lot of suffering here? All right, what is the cosine?
-4/5.
Okay, what's the tangent?
3/3/4.
What's the secant?
The inverse of the cosine.
Yeah, -5/4.
It's not the inverse.
Sorry, the reciprocal.
Yeah, no, that's one that, my hackles right, yeah. If you mean inverse, say inverse, if you mean reciprocal, say, but there is never gonna be a time the rest of your life, I'm not joking. There is never gonna be a time when you're gonna get the same answer. In fact, one's an input, one's an output. That's how far apart they are. One's an input, one's an output, they're never gonna be the same thing. All right, this is the reciprocal of which one?
The cosine.
Cosine.
Reciprocal of the tangent. And then the reciprocal of the sine.
Did you have to ever find the angle?
No.
Why was the quadrant important?
The negatives.
Yeah, the plus or minuses would have been different if I'd been in a different quadrant. Was that hard? Probably not. Do you guys remember doing something like that at some point in your lives?
Mm.
Yeah, that was pretty simple. That wasn't bad at all. All right. It's the being able to work through this is really, really important. So now I'm going to do a slightly higher level one. I want the cosine of the inverse tangent of 4/7. Is my answer an angle or is my answer a ratio?
Ratio.
Yeah. Wait.
This is actually the same as this question. I asked it differently, but it's really the same problem. In this question here, I asked you all of these things, but what I was really asking you to do is find the cosine of the inverse sine of 3/5. That's what this is. This is the tangent of the inverse sine, and so on and so on and so on. Okay? Now, I don't need to tell you the quadrant because the inverse tangent, it's automatic. Inverse tan returns which two quadrants?
1 and 2. Or
1 and
1 and
4.
4.
1 and 4. When is the tangent, the inverse tan of this ratio produces an angle, but the ratio is positive, so which quadrant must it be in?
1.
First. If this had been negative, then I would have had to be in the fourth quadrant. This is how you determine quadrants now, by the plus or minus, okay? So no matter what, my angle is in the first quadrant. So I'm going to draw a picture There. Now, this is your theta. Inverse tangent of a ratio is producing the angle. That's my theta. Would it be correct to say then that the tangent of theta equals 4/7? Is that a correct statement then? What do you think? Yes?
Mhm.
Yes. That, by the way, it's huge that I see that, because now you see, oh, it really is the same question as this one. Why do I need that? Because I need the picture. I need the appropriate picture. So what goes where?
Seven's the bottom, and then 4 is the right side.
Because the tangent is the ratio, right? This is the TOA. And then what's going to go here?
Root 65.
So 49 plus 16, 65, so the square root of 65. Everybody cool with that? I haven't answered the question yet, but everything I need is right in front of me. I now need the cosine of this angle. What would the cosine be?
7 over root 65.
7 over root 65. Beautiful. Oh, here. Is it possible I made a mistake? Is it possible you made? It's always possible you made a mistake. Can I check this? When I do this on my calculator, I'm never going to see that number. I'm going to see decimal equivalents. But can I compare decimal equivalents? Yeah, so what I would do on my calculator, literally from left to right, type in cosine tan inverse 4/7. And you're going to see a decimal on your screen. So everyone do that for a moment. Do the cosine of the inverse tan of 4/7 and tell me what decimal you see. There's no way in the world you're recognizing this decimal as being anything.
0.86.
Okay, 0.8 okay, so just remember the first couple decimals. All right, now do, on your calculator, do 7 divided by root 65. I'm showing you the ultimate lazy here.
Basically the same.
Is it exactly the same? You didn't memorize the whole thing, but you remember the first couple places. Are they the same?
Yes.
Yeah.
Yeah.
Is there any possibility it's wrong? No. None of them are the same. Well, they're almost the same. No, they are the same or they're not the same. They're not almost the same. So I just gave you a quick check. But the problem with doing this directly on my calculator, all I'm going to get is a decimal equivalent. I'm not going to get that, and that's the answer I want. But I can check using my calculator, using the inverse key. Does it matter whether I'm in degree or radian mode? No, because I never asked for the angle. I only asked for the ratio, and the ratio is the same regardless if I'm in degrees or radians. So that's sort of a little safety net there. You like that? Yeah.
Would you want us to take the square root out of the denominator? Or do you care?
For what reason?
Just, I don't know, my pre-calc teacher used to do that.
No, actually, that's the most, well, I'm glad you brought that up. That's not really it's less of a thing in this class as it is in the higher classes, because in Calc 3 they deal with vectors and they have to deal with unit vectors, so the answer to every question has roots in the denominator. And I'll go out on a limb and say probably everybody in the room was told wrong information. And I'm not saying that jokingly. It's reasonable that everybody here learned it incorrectly because of one simple vocab word that most people don't even know what it means, the term rationalize. This is the right question to ask, because the question often is, am I done? Do I need to keep going? The only real rule when you have a quotient is that you've reduced as far as you can reduce. There are no common factors left. Do we agree with that? No one would write a final answer, 4 divided by 8, because I can keep going. But if my answer was 4 divided by 9, there's nowhere to go, so I'd leave that. If I needed a decimal approximation, depending on the class, I can always give a decimal. That's not the question. The question is, when roots are involved, how far do you take it? So, let me ask you a question. You just done the cosine of pi over 4, or 45 degrees. You got that. Somebody else gives me that. Somebody else gives me that. Tell me about these three answers.
They're the same.
They're all exactly the same answer. You've been told all your life you're supposed to rationalize. I'm guessing no one actually has ever in their entire life rationalized. Because only one of these is rationalized, and it's the only one no one ever is going to use. There's only one that's rationalized. Anybody know which one it is?
Third one?
The third one. The term rationalize means there's no root in the quotient. It has nothing to do whether it's numerator or denominator. You can't have a root in the quotient if it's rationalized. The reason you learned rationalization is kind of archaic now. Okay, how many have had an algebra course recent enough that you actually remember something about it? Like when you looked in the back of the book, it had a table of logarithms and a table of square roots. You guys remember that? It'd give you like 5 decimal approximations of both roots and radical logs from 1 to 100. Because these books were written before the days that handheld calculators were cheap, affordable, and actually did logs. I mean, the ability to do a log on a calculator didn't exist until the 90s. I mean, the ability to graph a graph on a calculator accurately really didn't exist till the 2000s, even though calculators had been around. The technology was really slow for a long time. The books were written in such a way that you didn't have it. So one of the problems, you guys didn't have to do this so much. You had to do this in class. Calculators didn't exist. I've been at Mesa so long. I was at Mesa many years before the internet existed. That's not a joke. Many years before there was the internet. Our computers didn't really do much. There was no internet, and the email, by the way, was still many years away after I started working here. So you had to take 1.414, blah, 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 and then do the long division. Does anyone remember doing something evil and hideous like this when you were kids? Did long division of stuff like this. That's awful. But if I did this one, or simply did this one, now my answer is 707 something. It's real fast and real simple. So part of the reason you did these, either one of these, was because now I could work with that horrible decimal that was handed to me, by the way. I didn't know where it came from. I got it out of the back of the book. It was a correct value from a table, but I didn't have a calculator. So it's way more practical to do this. That's the reason you learned. Plus, the other reason you learned was so you could add like roots. But in actuality, now that everyone has calculators, there's no benefit either way as long as it's reduced. So I'll go out on a limb. The only answer you should have never given in your entire life is that one. Because that's the only one that's not simplified at all. Let me ask you a question. I always have fun with this one. I'll write it in the middle. I'm sorry if I'm blowing your mind, but I'm telling you the only way it's ever been done, that when calculators were invented, everybody changed the rules and they went backwards, and now wrong answers are considered the best answer. No, that's the only one that I would never do. I would never do that one. Why? Because it's the only one up there that's not actually simplified. If I wanted to do this, is this an acceptable final answer? A lot of people say, no, I can't have that radical on the bottom. Actually, you can't. But, so you're told not to do that. So you did stuff like, well, first of all, let me write it like this. Might make it easier. Let me do top and bottom by the square root function. Is that legal? Same as going like this. So now what do I got? X to the 1/2 over x, which is the same as root x over x. But because I can write that as an exponent, I now have an x on top and I have an x on the bottom. Absolutely, I have to combine these. I'm supposed to subtract the exponents. And now that's x to the negative 1/2, which is 1 over x to the 1/2, which is 1 over root x. So I just filled up an entire page to take the first thing I started with to prove that that is the only simplified answer. Pretty ridiculous, huh? I have people do this one all the time. 1 over root x is the only simplified answer I could possibly have. I went backwards here. I just made this way more complicated. Why is this not simplified? Because you have 2 to the 1/2 over 2 to the first, which is equal to 2 to the negative 1/2, which is equal to 1 over root 2. Mathematically, it's a simple proof that that's the simplified version. That is not. So, does it matter if you have a root on top and bottom? Never. Will anybody in a math or science class ever mark you wrong? No. Is there any advantage one way over the other? It can be. Depending on the rest of the problem and what other roots you're dealing with, and what are you going to do with them in the long run? Are you going to multiply them further, or are you going to manipulate them? You guys are all going to be working with vectors in a short time, a couple of semesters. And what order you do things and how far you take things is really dependent on how you're going to use it later. Any of those versions is absolutely correct, because none of them can be simplified further except that one. But since most of you were trained that I always have to do this, and now you see why I laugh at that. This is the only one that's the bad answer. You have the same factor on top and bottom. You're supposed to cancel. I mean, if those were x's, you know, yeah, I got to cancel. When can I lost the answer. It was 8 over root 65. When could I cancel?
7.
or 7 over 65. If the root 65, for example, had a factor of 7 in it, then I might be able to do some canceling. But since it didn't, I just walk away. Is it ever necessary to change that answer to a decimal? Not really. The reason is anybody can take an irrational number and give a decimal approximation. But you can never take the decimal approximation and work backwards and say where it came from because it's already been rounded. So if you're going to give a decimal, it's always give the answer and give a decimal just to be safe. But in the math class, we don't need the decimal answer. But if you're in chemistry or physics, that's the answer they want. Okay, and like I said, you know, when you go down to Home Depot later on and you need root 2 feet of wood, there's no root 2 marking on the measurement, right? I need a decimal at some point. So there are practical times for decimals. Now, the reason we're reviewing all of this is not so you can do it's not so you can do that problem. Not at all. No, not even a little bit. We're doing this. I want to do the cosine of, how about the inverse sine of, how about, I don't know, 2/3 x. I just threw something else at you that you've never seen in your entire life, maybe. I just made this kind of different. What did I throw at you?
X.
Yeah, and by the way, from this point on, you're only going to see problems of this nature with variables in it. You're never going to see them with numbers. Why? That doesn't require any math skill. I just need a cheap calculator. So tell me about my answer. Is my answer going to be a number?
No.
Probably something x-ish. You agreed? Ooh. So how the heck am I supposed to do this one? Same as the way we did the other one. Draw a picture. What quadrant am I in? I don't know. It's either what or what?
1 or 4.
1 or 4, because inverse sine returns 1 or 4. And by the way, my final answer will be bared out, so don't worry about that. I'll draw a first quadrant angle, but then I'll also do it in the fourth in a moment. But I'll start with the first quadrant angle. How do I get theta? What is the sine of theta? 2/3 x. Now, that is correct. I don't like 2/3. 2/3 x, if it was my final answer to a question, is a good answer. But I need something very SOHCAHTOA-ish. I need a clear quotient. Do you agree that I need a clear quotient? So how do you want to say it?
2x over 3.
Yeah, this is one of those rare times I'm actually going to go backwards. And now I have a very clear numerator and denominator when I do my SOHCAHTOA. Is it SOHCAH or TOA, by the way?
So, opposite of the
So what goes where?
2x is opposite, so that's there, yeah.
Vertical?
Yeah. And
Where's the 3 go?
diagonal.
Now stare at that picture for a moment. Is the sine of that angle 2/3 x?
Yeah.
But by writing it this way, by the way, this is not incorrect. And I've had people say this is the way they learned it. They said, I put a 1 here and a 2/3 x here, and that's absolutely correct. But it makes this one kind of ugly, and it makes my answer really ugly, and I have to do all sorts of extra algebra to get to the final. I'd rather do this. Then I'm not creating an issue. It is absolutely correct to think unit circle. But your final answer is now going to require a significant amount of simplification because you're going to have roots of fractions in numerator and denominator at that point. That's just messy. What goes there?
It's square root 9 minus 4x squared.
Beautiful. All right. In this picture, the sine of theta is clearly 2/3 x, and now all I want is the cosine.
The square root of 9 minus 4x squared, all over 3.
All over 3, or probably better, just how about a third? Now, wait a minute. I drew a first quadrant picture. Didn't we say this could have been a fourth quadrant picture?
Yes.
It could have been. So does that change everything? No, I get the same answer. Why? Because cosine is positive in both the first and the fourth. So it's more of a, yeah, it actually usually won't matter. So I tell people just draw the picture in the first quadrant unless you have reason to believe otherwise. And you're gonna get the right answer. Isn't that cool though? My final answer is a function. And the reason it's necessary for us to do this now is what we're gonna do next day is derive the derivatives of inverse sine, inverse cosine, inverse. We're gonna derive the derivatives of all of them. But in order to do so, I have to be able to manipulate things that involve variables, not just numbers, because those answers are gonna show up. It's really beautiful how it works in the end. Is this hard?
No.
Yeah, it's a little bookkeeping. Let's keep going. I want you to feel comfortable. This is not calculus. We're not doing any form of calculus right now. We're just reviewing the inverse trig functions and their relationships primarily with each other. That's a biggie. All right, so let's do, how about the inverse sine, let's see, inverse sine of, how about 1 over x, and then I want the tangent of that. This one looks a little scary. So what I want you to do is draw the picture. Draw the associated triangle. If it helps, always remind yourself. I'm finding the tangent of an angle, my answer is a ratio. So the inverse sine of this thing is the angle. So when I draw my picture, I'm actually drawing the sine of theta equal to 1 over x. That's really important that I see that one.
So tangent will be 1 over,
Well, let's
Oh.
fill the picture first.
the
What goes
right's
where?
1,
Vertical is 1.
hypotenuse is x, the bottom is root x squared minus 1, and then tangent would be 1 over root x squared minus 1.